This is Babitha, working as Assistant Professor in the Department of ECE in Institute of Aeronautical Engineering. In this session, I am going to discuss problems related to the field effect transistor as well as common source amplifier. So, in this, we are going to discuss the problems related to find the currents as well as voltages related to the field effect transistor, and also the problems of common source amplifier, that is one of the configuration of the FET transistor here. And in this, we are going to calculate the input impedance, output impedance, as well as voltage gain of the common source amplifier. And along with this, we may also calculate the overall voltage gain of the given circuit. So when we are going to solve the problems related to the common source amplifier, while designing the common source amplifier, we may utilize the different types of biasing techniques. That may be the fixed bias circuit or self-bias circuit or voltage divider biasing circuit. So if we go with the fixed bias common source amplifier, we are having the three parameter values or formulas. We are having input impedance Zi, output impedance Z0, as well as voltage gain AV here. So if we go with the exact analysis, we will get the input impedance is equal to the gate resistance in both the cases, with exact analysis, as well as with the drain resistance is greater than the RD resistance. And if you go with the exact analysis to find the output impedance, that is the parallel combination of RD as well as RD here. And if you go with RD is far greater than RD, means we will get it as capital RDR, drain resistance. And while coming to the voltage gain, it is minus GM RD parallel with RD. And if small RD is far greater than capital RD, in that case minus GM RD here. It is the approximate model values. These are the approximate formulas and these are the exact formulas. So depending upon the given parameters in the problem, we have to go with either exact analysis or approximate analysis here. And when we go with the self-bias circuit, and here we are having the exact analysis as well as approximate analysis here also. In this case, we are going to consider the bypass source resistance as well as unbypassed source resistance. When we are considering the bypassed source resistance, means we will get these particular formulas, and when we are going with the unbypassed source resistance, we will get these particular formulas. We are going to utilize these particular formulas. And next, if we go with the voltage divider biasing, in this case also we are having two cases, bypassed source resistance as well as unbypassed source resistance. So depending upon that, we can utilize any of these formulas. And while calculating the FET parameters, we are going to utilize the formulas. To find the pinch of voltage of the FET, we are going to utilize Q into Nd into A square by 2 into epsilon S is the formula to find the pinch of voltage. And similarly, to find the drain current, it is IDSS into 1 minus VGS by VP whole square. So these are the formulas we are going to utilize to find the FET parameter values. So while coming to the first problem, that is related to the problem of FET circuits, not the common source amplifier, only FET circuits we are going here. In an N-channel FET, the effective channel width is 3 into 10 power minus 4 centimeters, and donor impurity concentration is 10 power 15 electrons per centimeters cube. In this case, find the pinch of voltage of the N-channel FET here. So before calculating the values, first of all, I am writing the given parameters here. The effective channel width. The effective channel width we are indicating with the small a, and that value is 3 into 10 power minus 4 centimeters. And next, donor impurity concentration we will indicate with capital M D, that is 10 power 15 electron per centimeter cube. So from these values, we have to find the pinch of voltage of the FET here. So what is the formula for pinch of voltage? I have just now mentioned Vp equal to Q into ND divided by 2 epsilon into A square. So this is the formula to find the pinch of voltage. Now substitute the values here. Vp is equal to before calculating the values, first of all we have to find the overall epsilon value, as well as we have to convert the A value into the desired parameter. So for that purpose I am taking where epsilon is equal to 12 times epsilon naught here. So that is 12 into epsilon naught value is 8.849 into 10 power minus 12. So if we simplify it, we will get it as, otherwise I am taking here it as it is. This is the epsilon value. And next, charge. Charge I am taking here it as 1.69 into 10 power minus 19 joules here. And next, donor impurity, given it as 10 power 15 electron per centimeter cube here. So if we convert it in meter cube, we will get it as 10 power 21 electron per meter cube here. Okay, and next, carrier concentration or effective channel width, we have taken here it as A equal to 3 into 10 power minus 4. So this one I am taking here 3 into 10 power minus 4 centimeters. If we convert it into meters, we will get it as 3 into 10 power minus 6 meters. Okay, so now by utilizing this epsilon as well as Q, ND and A values, we can find the overall pinch of voltage of the FET. So that is Vp is equal to Q into, that is 1.6 into 10 power minus 19 into 10 power 21 into 3 into 10 power minus 6, this is A value, divided by 2 into 12 into 8.849 into 10 power minus 2. So if we simplify this, we will get it as 6.87 volts is the pinch of voltage of the given N-channel FET here. So while coming to the second problem, it is a self-biased P-channel MOSFET has a pinch of voltage Vp equal to 5 volts. So the pinch of voltage given it as 5 volts, and IDSS, the drain current at saturation level value is 12 milliamps, and the supply voltage is 12 volts. Vs equal to 12 volts. So from this we need to calculate the values of drain resistance and source resistance, so that the drain current is given as 5 milliamps and the drain to source voltage is given as 6 volts. So from these given values, we have to calculate the drain resistance as well as the source resistance of the P-channel MOSFET here. So in order to calculate these drain resistance and source resistance, I am taking the formula of drain resistance of the MOSFET here. So the drain current formula here it is IDSS into 1 minus ID into RS by Vp whole square. So this is the formula for the drain current. So here substitute the given values. ID current value is given, that is 5 milliamps, 5 into 10 power minus 3, and the IDSS value is 12 milliamps, 12 into 10 power minus 3, 1 minus, again drain current is 5 milliamps, we don't know the value of RS, and the Vp value also given, that is 5 volts. So these are the given values. From this we need to calculate the source resistance. So here we will get it as, if we take this term into the left side, 0.46 is equal to 1 plus 1 into 10 power minus 3 into RS. Okay. So from this, if we simplify, we will get the RS value as 764.1989 ohms. So this is the source resistance. This is the first parameter asked in the problem. And next we need to calculate the drain resistance RD. So in order to calculate the drain resistance RD, I am considering the P channel MOSFET here. So the P channel MOSFET, to find the RD value, I am considering the P channel MOSFET. Okay, and it is having the capacitor, resistor, and the source capacitance CS as well as source resistance RS. And here we will provide the VDD, that is RD resistance we need to calculate, and here it is input voltage Vs, and here we need to find the output voltage V. Okay, it is the P channel MOSFET. So this is the gate resistance RG. So by applying KVL at output side, I can write it as VDD, and drop across RD is ID into RD minus the drop across drain to source is VDS is equal to 0. So here VDD value given it as 12 volts minus drain current is 5 milliamps into RD, and VDS is given as 6. So if we simplify this, we will get the drain resistance value as 1.2 kilo ohms. So this much drain resistance is required to design this P channel MOSFET. And next, well, coming to the next problem, the FET shown in figure has IDS is equal to 12 milliamps and VP equal to 5 volts. Calculate the quiescent values of drain current, drain to source voltage, as well as gate to source voltage. So the circuit given in the problem is, this is the circuit given in the problem itself. .3 kilo ohms, and here it is VDD, and the source resistance is 1.2 kilo ohms. And here it is 1.5 mega ohm gate resistance is, and here we are applying the input voltage, and again through the coupling capacitor we are measuring the output voltage. Here it is 0.05 microfarads, and here it is this capacitance value is not given. This is RG value, RG equal to 1.5 mega ohms. So from this circuit, we can able to get the values of gate resistance 1.5 mega ohms, and the drain resistance value is 3.3 kilo ohms, and the source resistance value is 1.2 kilo ohms, and also given it as the drain saturation current as 12 milliamps, pinch of voltage of the FET is 5 ohms. So from these we need to calculate how much drain current which is flowing in the output terminal of the FET, and how much drain to source voltage required to flow that much amount of current, and how much amount of gate to source voltage required to run this particular FET here. So to calculate that values, I am taking the simplified version of this given circuit here. I am drawing simplified circuit. So in that we are taking only the drain resistance and source resistance RS, RD. Here we are applying VDD, and the gate resistance RG. It is nothing but we are not considering the capacitors into the circuit while calculating the parameters. So this is 1.5 mega ohm given in the problem itself. It is 3.3K and it is 1.2K here. This is drain, source, gate terminals of the FET. Okay, so to find the drain current, how much which is flowing in the circuit, I am applying KVL. Apply KVL at input side or input circuit. So if we apply KVL at input side, we will get it as VGS. VGS is means this particular voltage between gate and source. VGS minus drop across source resistance, that is IS into RS, is equal to 0. So across input side we are having only this voltage and drop across the source resistance RS. So here VGS we can write it as IS equal to RS, and we can also write it as ID into RS. Why? Because here the drain current is approximately equal to the source current here. Why? Because the drop across the gate terminal is very less. So because of that reason we are writing VGS is equal to ID into RS. So if we solve this particular equation, so I am taking here it as the equation 1, and by utilizing this I'm going to calculate the drain current ID. So we have ID equal to IDSS into 1 minus VGS by VP whole square. So substitute the value of VGS here. If we substitute this value here, we will get it as ID equal to IDSS 1 minus ID into RS by VP whole square. And after substituting all the given values, we will get the drain current as 2.33 milliamps or else 7.45 milliamps. Okay, so we have to calculate the VDS value by using 7.45 milliamps. Why? Because this is the highest value compared to this one. So we will check for this. If it is not coming right value, means again we need to go with the next value, 2.33 milliamps here. So to calculate VDS, I'm taking VDD minus the drop across both the resistances, drain resistance and source resistance, that is ID into RS plus RD. Okay, so here the drain voltage given it as minus 18, and the drain current we are taking here it as 7.45 milliamps, and the source resistance is 1.2 kilo ohms, and the drain resistance is 3.3 kilo ohms. So if we simplify this, we will get it as 15.525 ohms. This is the drain to source voltage required for the circuit. So this much drain to source voltage we are getting here, but in the case of a given FET, this value must be negative here. This value we should get in the negative value. So that's why again we have to check with drain current is equal to, second value is 2.33 milliamps. Okay, drain current I am taking here it as 2.33 milliamps. If we consider this value, we will get it as VDS equal to VDD minus ID into RS plus RD. That is nothing but minus 18 minus ID value. Now here it is 2.33 into 10 power minus 3, and RS is 1.2 kilo ohms plus RD is 3.3 kilo ohms. So if we simplify this, we will get it as minus 7.515. So now we got it is in negative form. So it is the correct value, but this one is wrong if we take ID as 7.45 milliamps. And also we need to calculate gate to source voltage VGS, that is ID into RS. Already we have calculated this value. We got VGS equal to ID into RS, and now we know the values of ID as well as RS. ID is 2.33 milliamps into source resistance is 1.2 kilo ohms. After simplification, it is 2.796 ohms. So this is the gate to source voltage required for the given FET. And we're coming to the next problem. The JFET shown in figure has a saturation drain current 8 milliamps. IDS is equal to 8 milliamps. And the pinch of voltage is minus 3 volts. And from this we need to calculate quiescent drain current as well as quiescent drain to source voltage as well as the quiescent gate to source voltage. So the given circuit in the problem is the FET with input source resistance as well as input capacitor and source voltage Vs. Okay, and along with this, the given it as the source resistance as 87 kilo ohms, and this value is 2.5 kilo ohms, and one capacitor is connected here, and it is minus 18 volts here, and here we are going to measure the output voltage. So this is the given circuit in the problem. So to find these quiescent values, we have to take the simplified form of this given circuit. So in that simplified form, we will remove the capacitors, input-output capacitors. This resistance Rs, and here we are having the drain resistance Rd also. Here it is 100 ohms, here it is 2.5 kilo ohms, and this one is connected here. Sorry, it is, we are providing the supply minus 80 volts here, and the gate current Ig is flowing here, and we are having VGS voltage here. So here we also have VGS is equal to minus ID into RS. In the previous problem, we have calculated this value. In the previous case, it is ID RS, but here VP value is negative, so that's why it is minus ID into RS. So ID value given it as 100, so minus 100 into RS here. So again we have the drain current formula. ID is equal to IDSS into 1 minus VGS by VP whole square. So substitute this VGS value here in equation 1. So if we substitute this VGS value here, we will get again drain current as 167 milliamps or 5.385 milliamps. Two values we are getting here. Again we need to check for both the drain currents which one is suitable for the circuit. So for that purpose, I am calculating VDS by using ID value as 167 milliamps. Okay, or else VDS from ID equal to 165 milliamps. So it is 167 milliamps. So VDS equal to VD minus ID into RS plus RD. So VD value given it as minus 18 volts minus of ID current is 167 milliamps, and RS value is 100 ohms, and the drain resistance value is 2.5 kilo ohms. So this value will get here it as minus 401.17 volts. VDS is minus 401.717 volts. So VDS can be greater than VDD here actually, but this value we are getting here it as less than VD here. So that's why again we need to check for ID equal to next value, that is 5.385 milliamps. we need to check with this particular value. So if we check with this particular value, we will get VDS equal to VD minus ID into RS plus RD. So that is minus 18 minus 5.85 into 10 power minus 3 into RS is 100, RD is 2.5, 10 power 3 kilo ohms. So if we calculate this, we'll get this value as 4.484 volts. VDS voltage is. So now VDS is greater than the VD voltage. And again we need to calculate the VGS voltage, gate to source voltage, is equal to minus 100 ID, that is RS into ID. So minus 100 into ID value is 5.85 into 10 power minus 3. So we will get it as minus 5.385 volts. So this much gate to source voltage required to run this particular FET. Until now we have discussed the problems related to the FET circuits, and next I am moving with the problems related to the common source amplifier here. A common source FET amplifier circuit with unbypassed source resistance has the following circuit parameters. Those are RD equal to 15 kilo ohms and the source resistance RS equal to 0.5 kilo ohms and the gate resistance RG equal to 1 mega ohm and the small RD value is 5 kilo ohms and the transconductance GM is equal to 5 millisiemens and the supply voltage VDD equal to 20 ohms. So from these given values, we need to determine the voltage gain, input impedance as well as the output impedance of the circuit here. Okay. So in order to solve this particular problem, first of all, we have to draw the common source FET amplifier with the given values. So for that purpose, I am drawing the common source amplifier. Here we are having the drain resistance RD equal to 15 kilo ohms and here VDD voltage, and also we are having the gate resistance RG is 1 mega ohm and here we will apply the input signal, and also the source resistance R is equal to 0.5 kilo ohms. And here we will measure the output voltage in the common source amplifier. So this is the common source amplifier, and next again we have to take the small signal model of this common source amplifier in order to find the amplifier parameters. Just know how we done in the case of bipolar junction transistor. So for that purpose, I am drawing the small signal equivalent model of this particular common source amplifier here. So for that purpose, first of all, I am taking the 3 terminals, gate, drain, source terminals of the FET. And for the gate terminal, what are the elements connected? RG resistance is connected. So that's why for the gate, I am connecting the RG resistance. And here we are applying the input voltage. And also between gate and source, we will apply the gate to source voltage. So that's why VGS. And across the output side, we are having the drain resistance as well as source resistance. And also we will get the transconductance parameter, that is GM VGS. Along with this, we are having the source resistance and the small RD values and drain resistance RD. So here ID current is flowing. So this particular total thing is the small signal model of the circuit. Small signal equivalent circuit. or small signal model of the common source amplifier. So here they given it as unbypassed source resistance RS. In the case of unbypassed source resistance RS, we are having different formulas, and if it is bypassed source resistance, in that case we have to utilize other formulas. So if suppose the small resistance value is far greater than the source resistance as well as the drain resistance. So in this particular case, the voltage gain AV is equal to output voltage by input voltage, that is equal to minus GM RD by 1 plus GM into RS. So this is the formula to calculate the voltage gain with unbypassed source resistance RS. So if we substitute the values, GM value is given it as 5 millisiemens and the drain resistance is 15 kilo ohms divided by 1 plus 5 into 10 power minus 3 into source resistance is 0.5 kilo ohms. So if we simplify this, we will get it as 21.42 as the voltage gain A. And next, if the drain resistance value is less than the sum of the source and drain resistances, in that case, the voltage gain formula is minus GM RD by 1 plus GM RS plus sum of both the resistances divided by small r. So this is the formula. So in this, again, we need to substitute all the values. It is minus 5 millisiemens GM is, and the drain resistance value is 15 kilo ohms divided by 1 plus 5 into 10 power minus 3, and the source resistance is 0.5 10 power 3 plus again source resistance is 0.5 into 10 power 3 plus drain resistance is 15 kilo ohms and small RD value is 5 kilo ohms. Okay, all the values given in the problem itself. So we will get it as 9.99 into 10 power minus 6 as the voltage gain if RD is less than RS plus RD here. And next parameter we need to calculate here, it is output impedance, that is Z0. The formula for output impedance Z0 is small rd plus source resistance of Gm RT plus 1. So this overall parallel with RT resistance. So if we substitute these values, RD is 5 kilo ohms, 5 into 10 power 3, and the source resistance is 0.5 kilo ohms, and Gm is 5 millisiemens, and RD is 5 into 10 power 3 plus 1. This overall parallel with 15 kilo ohms. Okay, so if we simplify this total thing, we will get it as 18 kilo ohms parallel with the 15 kilo ohms. So obviously, if we are taking two unequal resistances as parallel combination, means always we will get the smallest value as the result. So Z0 is nothing but 15 kilo ohms here. That is Z0 equal to 15 kilo ohms. So this much voltage gain as well as output impedance we can expect from the given common source. And while coming to the next problem, draw the low frequency equivalent model and calculate the voltage gain of the circuit shown in figure. Assume all capacitors to be large. So here the circuit given in the problem itself, that is FET amplifier, common source amplifier with gate resistance RG 1.2 mega ohms, and here input voltage is given, and also the source resistance RS, as well as one more resistance is given 470 ohms, and drain resistance RD equal to 4.3 kilo ohms, and here the supply voltage VDD is 24 volts given, and the coupling capacitor V0, and here it is 120 ohms, and the bypass capacitor is also given. So for this given common source amplifier circuit, we need to draw the small signal equivalent circuit by considering all the capacitor values are large. So for that, to draw that circuit, I am taking the low frequency equivalent model. The low frequency or small signal model, low frequency equivalent circuit of the given common source amplifier. So in that case, to draw this again, we require the gate terminal, drain terminal, and here it is the source terminal. So what are the elements which are connected between the gate and source? We need to draw here. So the RG resistance is given. So first I am drawing the RG resistance with the value 1.2 mega ohms, and the input voltage is VI, and also we are having GM VGS, and the small RD resistance if we take the body effect into consideration, and the source resistance is 120 ohms here, and also the drain resistance RD is 4.3 kilo ohms, and here we'll measure the output voltage V0. So this is the small signal equivalent circuit of the given common source amplifier. So this particular circuit showing that it is the self bias having partially bypassed source resistance here. So in that case, we have to use the self biased common source amplifier formula here. In that case, if we consider that particular formula from the self biased table or from the table 2 given in the previous slides, from table 2 I am writing it is minus GM RD divided by 1 plus GM RS into RS plus RD by small RD here. So now substitute all the values here. GM value given it as minus 2.5 into 10 power minus 6, and the drain resistance is 4.3 kilo ohms, and again GM value is 2.5 10 power minus 6, and the source resistance is 120 ohms. Again source resistance is 120, and the drain resistance is 4.3 kilo ohms, and small RD value is 50 kilo ohms. So if we simplify it, we will get it as minus 10.75, 1.3884. So the overall value is minus 7.743 as the voltage gain for the given common source amplifier. So from the given common source amplifier, we have drawn the small signal equivalent circuit. It is the partially bypassed common source amplifier with the self-bias configuration. So while coming to the next problem, draw the small signal equivalent circuit for the amplifier shown in figure. Derive the expression for voltage gain V0 by Vs, and all capacitors to be arbitrarily large here. So to do this, first of all I am showing the circuit given in the problem. This is the circuit given in the problem with drain resistance RD and source resistance RS and the bypassed capacitor CS, and here plus VDD supply voltage, and along with this two resistances R1, R2, and also the coupling capacitor CI or C1, and the source resistance RS and the source voltage Vs is given, okay, and also the gate resistance RG given in the problem. RG also given in the problem here. And to measure the output signal, again coupling capacitor C2 is connected here. So this is the circuit given in the problem. From this circuit, we can say it is utilizing the voltage divider biasing. Why? Because we are having two resistances R1, R2 in potential divider form. So that's why we can say it as this is the common source amplifier with the voltage divider biasing. So in order to find the expression of V0 by Vs or overall voltage gain, we have to utilize the formulas of voltage divider biasing common source amplifier. So before going to that, first of all, we have to draw the small signal equivalent circuit, and then again a simplified circuit for that small signal equivalent circuit, and from that we need to find the values. So for that purpose, first of all, I am drawing the small signal model of the given circuit. So again we are having the gate, drain and source terminals, and for the gate and source we are having the RG resistance as well as the parallel combination of R1 and R2 resistances, and also the source resistance and the supply voltage Vs is connected between the gate and source here. And between drain and source we are having GM-VGS and the RD by considering the body effect, and the drain resistance capital RD and the load resistance RL. Here we'll measure the output voltage V0 here. So in order to find the given parameter, again I am simplifying this circuit as simplified circuit. I am drawing here it as just again I am taking the three terminals, gate, drain as well as source terminals. Okay, and here these three resistances I am taking. Here this is the RG and these two R1, R2 are in parallel combination. So I can write it as RG plus R1 parallel to R2. So I am replacing it with the single resistance with RG plus R1 parallel with R2 here. So this overall I can write it as RG dash, and this source resistance RS as well as source voltage Vs I am keeping as it is. And while coming to the output side, this GM-VGS is as it is, and these resistance, the body resistance, we cannot consider it into the normal resistances, so I am keeping as it is this one also. But these two resistances again are in parallel, so I can write it as RL dash equal to RD parallel with RL, the parallel combination of these two resistances. So here it is V0 voltage. So this is a simplified circuit. So from this simplified circuit, we can calculate the gain value. So the gain value AVS, the overall voltage gain is AVS. So first of all, I'll calculate only voltage gain. AV equal to output voltage by input voltage V0 by Vs. So I can write it as V0 by Vi into Vi by Vs. So here V0 by Vi is nothing but the normal voltage gain. This Vi by Vs we need to calculate here. So from this particular figure, I'm writing, or I'm taking here it as, this is figure A I'm giving, this is figure B, and this is figure C. So from figure B, I'm writing V0 is equal to minus GM VGS and RD parallel with RL dash. That is nothing but the overall parameters which are present in the output side. This GM VGS, RD parallel with RL dash. Okay, and here we know that Vi is nothing but VGS. The input voltage is nothing but the gate to source voltage here. So if we substitute this VGS is equal to VI here, we will get it as V0 equal to minus GM VI RD parallel with RL dash here. So from this I can write V0 by VI equal to minus GM RD parallel with RL dash. So we got the value of V0 by VI. And next we need to find the value of VI by VS to calculate overall voltage gain. So here VI is equal to minus VS into RG dash by RG dash plus RS here. That is from the input side. From the input side, you can write it as this particular value. This resistance as well as this resistance and this voltage source is present in the input side. So from that we are writing here it as Vs into opposite resistance, that is Rg dash by overall resistance Rg dash plus Rs, that is using voltage division rule. So here we can write Vi by Vs value as minus Rg dash by Rg dash plus Rs. So now the overall voltage gain AV is equal to V0 by VA value we got here it as minus GM RD parallel with RL dash into this value VA by VS, that is minus of RG dash by RG dash plus RS. So we can write this value as AV equal to minus GM RD, and here RL dash is nothing but RD parallel with RL. So that's why I'm splitting it as RD parallel with RL into RG dash is nothing but again RG plus R1 parallel with R2 at input side. Okay, divided by RG dash is again RG plus R1 parallel with R2 plus source resistance Rs. So this is the overall voltage gain of the given circuit here. So in this way we have to find the overall voltage gain. Suppose instead of giving direct resistance values here, if we give the values, just we need to substitute that values here. From the given circuit, first of all we have to draw the simplified equivalent model or hybrid equivalent circuit, and after that again further we have to simplify it with the similar type of resistances we have to observe in the input side as well as the output side. Then we can simplify the circuit, and after simplifying the circuit we have to go with the analysis to find that. Again we are going with to find the overall voltage gain. We have taken V0 by Vi as well as Vi by Vs, and we have calculated these two values, and finally we substituted the two values to get this final overall voltage gain. So in this session we have discussed the problems related to the pinch of voltage as well as drain current calculation of the field effect transistor, as well as in the common source amplifier we have calculated different parameters: voltage gain, input impedance as well as output impedance, and also we have seen the problems related to how to draw this simplified hybrid equivalent circuit for the common source amplifier, and how to find the overall voltage gain from the simplified circuit. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.